Okay, thank you very much. Thank you also to the organizers for the invitation. I'm sorry I had to miss most of it because of the overlap with the other workshop that you saw in the discussion yesterday. But since I arrived, all I've heard are good things about the conference, so I'm sure it has been a success. Thank you for putting this together. So my plan today is to talk about this recent work. Let's see this. No, good. Based on this work with Cody, Miguel, and Kumru. Okay, thank you. About finiteness, the desert, and the swampland. Okay, so finiteness is a recurrent topic both on the swampland program, geometry of the string theory compactifications. We talked many times, we expect finiteness of vacua, of Calaveras, of number of fields, of U1, the rank of gauge groups. And from the swampland perspective, it's even, I would say, it's the most basic feature that we expect that distinguishes the landscape from the swampland, that we expect that the landscape is finite. So there is just a finite number of effective field theory that can arise from quantum gravity, equivalent from string geometries that we can have, while the swampland is infinite. We can have infinitely many theories that are not consistent with quantum gravity. So in a more concrete way, in this paper with Jutta, Miguel, and Kumrun, we define this finiteness in this way, although, of course, this has been discussed many times in the literature in the past. The idea is that we expect to have a finite number of low-energy effective field theories after weak quotient by the moduli spaces that are consistent with quantum gravity and are valid at least up to some finite energy cutoff. Now, we emphasize this condition that they are valid up to some finite energy cutoff because it's important to get rid of all the asymptotic tails that we can have at infinite distance. So let me just mention that this was motivated by thinking of finiteness of quantum gravity amplitudes, although my talk is not going to be about this. But for example, if you think that you compactify two dimensions in an arbitrary manifold, the wave function would spread over all topologies, and this would give rise to a divergent partition function if you have infinitely many vacua. So it's just some argument that if we want to have finiteness of this partition function, then we should have only a finite number of vacua. And in the case of ADS, the finite energy condition is consistent with the fact that when we have all these, I don't know, like for example, ADS 5 crosses 5 examples, we can have an infinite family of vacua because we can have different values of the flux, but they are changing the cosmological constant in such a way that there are also other towers of states that become light, so the cutoff goes to 0, and therefore for a fixed value of the cutoff, there is only a finite number of vacua that are valid. Okay? So this also goes on the lines of this proposed conjecture by Dieter, Eran, and Kumru. And in the case of Minkowski, sometimes we even, it's not only that we get a finite number of vacua below a certain cutoff, but we can get stronger results. Like, for example, there is all this body of literature trying to constrain the rank of the gauge group in theories with 16 supercharges to try to classify what are all the possibilities. And in green, so this is in terms of the number of the dimension of the space-time, okay? And this R is the rank of the gauge group. So in green are those possibilities which we know how to realize in string theory. And in red are those that are not consistent because maybe they have some anomaly or they cannot preserve that much supersymmetry. And in yellow are those CFTs which seem fine, but still we don't know how to arise. And in recent years, what people are showing is that they all become red if you apply some swampland criteria, like the absence of global symmetries. Okay, so this is an example in which the rank of the gauge group is actually upper bounded, so that you really have a finite number of things. Okay, so these were just examples. What I want to focus in this talk is that if we have a finite number of quantum gravity vacua, in particular, we expect that this implies a finite number of massless fields, okay? Because otherwise I can just construct more and more vacua just by changing the number of massless fields. And in the context of Calabi manifolds, right, this maps very nicely to the expected finiteness of Calabi no? To have a bound on the Hodge numbers, which corresponds to a bound on the number of massless modes. So the question that we wanted to address in this paper is whether we can put an upper bound for the number of massless modes in a consistent theory of quantum gravity. Yes?
Are you proposing like some other, like if I define quantum theory of gravity from a CFT field, presumably every CFT defines some quantum theory of gravity because it has a massless spin to the degree of freedom, it's either complete and it's quantum. Well, certainly I can think of an infinite number of CFTs, just the three boson.
Yeah.
To the power n. I mean, what is it?
But that's why, I mean, we have to map to a holographic dual, and that's why, like, for example, in the ADS5 crosses 5, right? You could also think of constructing different operators, but there will always, from the bulk perspective, there is no infinite family, there is not infinite number of massless modes that you can have, or even massive, right? Because the cutoff is going to 0. Here I'm thinking of holographic duals in general.
If I just define, is this like an Einstein gravity? You need an Einstein gravity?
Yeah, I think, exactly. When I say holographic, I mean Einstein gravity, because part of my, I mean, we can think whether it could be more general than that, but part of the arguments or why we think that this could be true is also related to the species bound and all these arguments based on black holes. And for that, you need to have an Einstein gravity dual, because the point is that if you have many fields, you would expect that gravity becomes strongly coupled, the cutoff goes to 0. And
Gravity vacua, you mean finite number of vacua that looks like Einstein gravity?
yeah, right now I'm thinking of EFT, that's what I put here. Like low energy effective field theories, yeah, so put weakly coupled to gravity, that yeah, can be UV completed. Like I need to have an EFT, okay? But maybe it's more general than that, but I cannot tell. I mean, that's another question. Okay, so as I was saying, I mean, how we can get a bound on the number of massless modes? Maybe the first thing one can think from a bottom-up perspective is to check if there is any problem with black hole entropy if you have many modes. Okay, so what I'm going to do is I'm going to review what would be the problem with the black holes, see that actually there is no problem if the cutoff goes to 0, and then try to study the question in concrete string theory compactifications. Okay, we'll go to the geometry and try to check if we can really put these upper bounds. Any other question? Yes. Yes. Yeah, doesn't matter. More? Okay. Good. Thank you. Okay. So when I say, okay, if I have many fields, I mean, don't I have a problem with black hole entropy? So I could think that, for example, I could impose that if I have a box of a size L, and I fit many states inside the box, the entropy of the box should not be larger than the entropy of a black hole of that area. Okay. So this is going to put a bound on how many states, how many light species weakly coupled to gravity you can put inside of the box before the system collapses to a black hole. So if you do the computation, one recovers the well-known species bound, which is that the number of modes of light species scales with 1 over the cutoff to the -2. Okay, where this cutoff is the smallest size of the black hole that you can trust in the effective field theory.
These are massless scalar fields. You cannot put them in a box.
When you cannot put them in a box. I mean, it's about the interactions, right? Like you could wonder whether maybe they found bound states and how you count them and so on. But here we are talking about weakly coupled, so you think that the interactions are suppressed, and then each of them counts as a different species as if they are point-like. You can just fit many of them in a box. And this would violate the entropy bound. unless indeed there is a relation between how many you can fit and what is the size, no? Like the smallest size of the box. And this is what is behind this species bound used by Niemark, Hamed, Bali, and company. But this is telling you that, okay, so the problem of having many fields is solved if the cutoff decreases in this way, if there is this correlation. Okay, so I can have an EFT with many fields as long as the cutoff becomes light. And in particular, I can even have infinitely many fields if I allow the cutoff to go to 0, okay, according to this. So there is no really problem with the black holes if I allow to have an EFT with an arbitrarily small energy cutoff. And this is precisely what we know happens at the infinite distance boundaries, right? Like when we go to the infinite distance boundaries of the modular space, we get all this infinite tower of states. And of course, we have many, many states. The typical examples are the compactification limit or stream perturbative limit. And it's what is behind the distance conjecture that probably you have discussed, that we get many light fields quickly coupled to Einstein gravity, and this is indeed associated to a breakdown of the EFT. Okay, so there is no lower bound for lambda. It can go to 0. And therefore, it seems that there is no upper bound for the number of fields. But we can wonder whether there is an upper bound for lambda. Okay? So instead of going to the boundaries, what I want to do here now is to go to the interior of the modular space. Okay? So I want to see whether there is an upper bound for this cutoff, so how much I can push it up, okay, which is going to happen deep in the interior, and whether this can give me any information about whether there is a bound on the number of massless modes, okay? Because this is where this bound will get more constraining, okay, when lambda is as big as possible. I will explain how we do it in practice. Okay, so what we are interested is determining the maximum value of the cutoff that is going to happen in the deepest interior of the modular space, and see how much we can push it and whether, as I said, this can help us to recover any bound on the number of modes. Okay, so how do we define this cutoff? So in the deep interior of the modular space, what we expect is to have what we call this desert scenario, in the sense that we are pushing up all the state as much as possible, right? And then typically what happens, we'll see that you have like some bunch of massless modes, and everything massive is pushed to very high energies. So in this scenario, the species scale, instead of being dominated by the asymptotic towers at infinite distance, is going to be dominated by the massless modes. And the goal is to determine this cutoff. Of course, I mean, in order to determine this cutoff, I should be able to know the full spectra and know what is the maximum cutoff, no? Like the mass of the first state. That's a very hard problem. I mean, we don't know how to resolve this in general for non-BPS states. So what I'm going to do in the practice is to focus on BPS objects. Okay? For BPS objects, we can keep track of the mass, and we can study what would be the maximum gap given by the BPS states. Of course, it could be that there are some states which are lighter, but at least this is going to give us an upper bound on this maximal cutoff. Okay? So we know that we cannot push it up higher than this. Okay? So it's an upper bound for the cutoff that we are looking for. Okay? Good. And with BPS, I mean also not only BPS states, but also states that could arise from BPS object wrapping some cycles. Okay? Okay, so what I'm going to do now is let's try to compute this. So let's take different setups, supersymmetric setups, and check what would be this cutoff depending on the level of supersymmetry. So the first case, of course, is to start with 32 supercharges, maximum we can have. And then here the story is simple and not very interesting because, I mean, we don't have many moduli, so in the end it's about the value of GS in type 2. In M theory, the gap is going to be set by the tension of the M2 brane, which is going to be of order 1 and Planck. And in type 2, it's going to be set also by M Planck, because this cutoff is going to happen at GS of order 1, right? Because here we already have these dualities, no? That if we go to GS going to 0, some states become light. If we go to GS to infinity, others become light. And it's in the middle where we can get this maximum gap. So let me go to some more interesting case. The next one would be 16 supercharges. It's a bit more interesting because now we have different types of VP states, although I'm not going to spend much time on this because the really interesting one is 8 supercharges, as you can imagine. But let me already, since this is a structure that will also appear later on, let me describe it already here. So if I think, for example, just to take an example, a compactification of heterotic string theory, the VP states, I mean, there are different types of VP states. They form a cone. And we have either field theory states, in the sense that we have VP states that can become massless at finite distance. Or we have the states that give rise to these asymptotic towers of states, like Kaluza-Klein, no? Or winding modes. And then we have black hole states that never become massless. Okay, so depending on what is the value of the left moving, right moving momenta, we can distinguish between some of them. And here, this is a plot in which we show just a circle compactification for simplicity. And this is the radius. And here you can see like the different towers. And the blue line is a field theory state that become massless at the self-dual point. So the gap is going to be given by the intersection between these field theory states and the asymptotic towers, in this case. And one can compute that it's around 0.25 string scale. So we can already push it a little bit below the Planck scale. OK, what happens now in 8 supercharges? So with 8 supercharges is the first case in which, due to the larger number of Calaveras manifolds, now we can really have a landscape of solutions and explore how the cutoff behaves in terms of the number of fields, of massless modes. So first, I'm going to estimate what this BPS gap is going to be, just by taking some assumptions about the intersection numbers, some genericity assumptions, and then we will go to a concrete Calaveras. Like we'll take actually 30,000 Calaveras and really compute what is the number and compare with the estimation. Okay. So now I have BPS states. They will come from some branes wrapping some cycles. And we can consider 6d equals 1, 5d, or 4d equals 2. And 6d equals 1, the gap will be set by BPS strings that come from DC branes wrapping some curves. And the tension is set by the Kähler parameters with the condition that the volume is set to 1. So this is in Einstein frame, okay, in Planck units. So as you can see, the exact value is going to depend on these intersection numbers. Okay? So if I assume that the intersection matrix grows with the number of massless fields, then one can estimate what is the point in the moduli space in which I'm going to get the maximal gap in such a way that the gap is going to scale as n to the minus 1/4. Okay, so this is just taking this assumption of how the intersection matrix grows with the Hodge numbers, no? With the number of massless modes. Now, if I do the similar thing in 5d equals 1, now I'm going to have BPS particles coming from wrapping M2 branes. And again, I can estimate what would be this gap if I put some assumption on the intersection numbers. And the result is that the gap goes as n to the minus 1/3. Okay, so you will see where I am going. If I do it now in 4d equals 2, now I have to go, it's better to go to the complex structure moduli space, so I have into account all the quantum corrections. BPS particles come from the DC branes. And doing the same type of estimation, one gets that the BPS gap goes as n to the minus 1/2. Okay, so if I recap of all these results, we are obtaining that by using this genericity argument about the intersection numbers, the gap scales as n, sorry, there's a type of -1 over d minus 2, okay? Where d is the number of space dimension. So it was 1/4, 1/3, 1/2. And this is precisely the species bound prediction, okay? So this naive estimation of the intersection numbers reproduces the species bound, which a priori seems fantastic. I mean, maybe like we are checking the species bound result with the string theory. The funny thing is that now we are going to really check, I mean, plug in real topological data from the Calaveras, and we are going to see that this estimation actually was too naive. And we are going to recover a bit of a different slope that will try to explain why it happens. Okay, so let's take real data. Let's take real Calaveras as a landscape of Calavera manifolds. In the case of 6n equals 1. As I said, like the BPS states are going to come from our BPS strings that come from the DC branes, wrapping the 2 cycles of the base. And I want to compute what is the tension of this object in Planck units, okay? So setting the overall volume to 1. Now, as I said before, like well, even if I didn't say, the charges, not every charge is going to correspond to a BPS state, but the BPS states form a cone because 2 BPS states are mutually BPS. So this is the BPS cone, and this cone of the BPS charges is also what is called in geometry the Mori cone, no? Because it's the dual of the Kähler cone, given by the condition that the tension of these strings is positive. So in order to estimate what is this BPS, this gap for the BPS states, I need to know the Mori cone. I need to know what states are BPS and therefore compute their tension. And this is in general a very hard question for any Calavera. I mean, we don't know the answer for any Calavera threefold. But in the case in which we have an elliptic threefold with a toric base, this was completely classified by Morrison and Taylor. Okay, so we have all possible toric bases, and this gives us a mini landscape of Calaveras in which we know exactly what the Mori cone is, and we can compute what is this BPS gap. So in particular, this is going to correspond to around 35,000 examples. So we designed some algorithm to compute this, which in the end, so what we are trying to do is to compute, well, to maximize the minimal value of the curves. Okay, so we push the tension of the strings as high as possible, while the overall volume is fixed. Since the volume is homogeneous on the volume of the curves, we can rescale things to translate this very complicated problem to something much more simpler to solve, which is to set all the volume of the curves to some fixed volume, at least 1, and then minimize the overall volume of the space. And by finding this minimum overall volume, then we get the maximum BPS gap. So in other words, what we need to find is the minimum value of the overall volume within the stretched Kähler cone, which is precisely defined as the cone where all the curves have volume at least 1. Okay? And this, one can show that this is going to happen precisely at the boundaries of this cone, because the volume will decrease as you decrease the volume of the curves. So what you need to do, you don't need to minimize anything. What you need to do is just to evaluate the volume, the overall volume in these boundaries and find the minimum possible value. So it's just to resolve some H1,1 equations. Okay, so this is the algorithm, and these are the results. This is the value of the BPS gap, so the tension of these strings, well, the square root of the tension, in terms of H11, okay, in terms of the number of massless modes in this case. So as you can see, there is some tendency. Okay, indeed, it decreases, like the number, the gap goes to 0 as h11 goes to infinity. But the power is a bit different. I mean, the volume scales as h11 to the 1/4, so that lambda BPS scales as 0.7. And well, before comparing to the species bound, let me remark that in these cases, the cutoff, especially for large H11, is set by strings, which are like these field theory strings, that they become massless at finite distance. And they give rise to these superconformal field theory points. So we have, I mean, they are non-mutually local, so it's when the tension cross at some point, this is the point in which we have this maximum gap. Okay, so if we compare this result with the species bound, what we are obtaining is a bigger slope. Okay, so this was the estimation from the species bound. That was also the result that we obtained from assuming that the intersection matrix is diagonal and just grows with the number of fields. But actually, it's a bit different. It has a bit of a bigger slope. So you could ask, okay, what's going on? Well, one can check that indeed what happens is that these intersection matrices are not completely diagonal. And also the entries are not exactly 1, so that's changing the estimation such that the volume grows faster than expected with H11. And you could say, okay, so what is the interpretation of this? Does it mean that this species bound is not a good bound in practice? Well, I mean, one possible resolution, well, I put here that a lesson before that, of course, we have to be careful with all these genericity arguments because they can give a different result. But let me talk about the resolution. So a possible resolution, the screen doesn't want you to see it. A possible resolution is that, of course, we are just focusing on BPS states. So, I mean, we could be missing other states like Kaluza-Klein towers that are non-BPS and other states that are lighter. So, I mean, maybe it was asking too much, to expect that it was just the BPS states which were going to reproduce exactly the species bound result, which doesn't distinguish between supersymmetry or non-supersymmetry. So one possible resolution is that, indeed, maybe there are other states that are lighter, like KK modes, and that are setting this species bound slope, such that the real cutoff is below what we obtain. Now, the point is that since they have a different slope, this possible resolution is only valid for some finite region, because at some points the curves are going to cross, and then the tendency is going to change. Like, you cannot explain it by saying that you have states that are lighter and that you have missed. So it could be that, I mean, since this is only works for this region until they cross, it could be that this gives and this is precisely, I mean, like we know that these elliptic Calaveras trifos are finite, like there is only a finite number of them. I mean, it's consistent as long as they are always on the left-hand side. So a possible solution of this different slope recovers the idea that might be an upper bound on the number of massless modes, so that I have to stop at some point. I mean, I cannot continue this forever, okay? So this would be a possible resolution. Just to conclude, how much? I think I'm almost 5 more minutes, good. Okay, fine. So I wanted to have, like before concluding, I wanted to mention some connection with the Tadpole conjecture. So let me remark that we are trying to go now to the deepest point in the modularized space. Of course, it's difficult to control, so that's why we're focusing on BPS states. But it can be interesting to learn different things. And one possible implication of these results, independent of the number of a bound on the number of massless modes, is a relation with the Tadpole conjecture. So the Tadpole conjecture was proposed as an abstraction to stabilize all moduli in flux compactification. So this is going to be a very quick review, so I'm apologize if it's not clear. You can ask me if you have any question. But the idea is that these people were proposing that if there are many moduli, it might not be possible to stabilize all of them in a flux compactification without violating the Tadpole conditions, okay? Because if you have many moduli, you need to put many fluxes, and since they are constrained by the Tadpoles, there is a tension there, which might be manifest when you have many moduli. So there's a lot of debate here. I mean, people are studying this, but it's interesting that it's actually connected to our computation because if I think, for example, if I think of checking this conjecture in the large complex structure limit of a type 2B flux compactification, the large complex structure limit maps to the stretch scalar con that I was talking about. And in order to prove this conjecture in this particular corner, no, in this particular setup, what one needs to check is how the flux number, okay, that is going to appear in the Tadpole, the flux number that's in this corner of the moduli space scales with the volume, how this scales with the number with H2,1, with the number of massless fields. Okay. So what, for example, Eric was doing in this paper is estimate how the overall volume was behaving with the number of fields so that one can check if the end flux is going to be smaller or larger than the contribution to the Tadpole. And if the volume scales linearly with the H2,1, then this conjecture is satisfied that you cannot really stabilize all the moduli. So this is exactly the same optimization problem that we were doing. Okay, so you try to find what is the minimum value of this volume that you can find in this stretch scalar con. In our case, we did it for 6 n = 1. Okay, so that means that the overall volume I'm talking about is actually the volume of the base. So it's not exactly the overall volume of the Calaveras, although, I mean, if you allow me to forget that for a moment, in our case was scaling with H11 1.4, so it was even bigger than what the Tadpole conjecture claims. So if the overall volume, not only the volume of the base, has the same scaling, this, I mean, provides some support for this Tadpole conjecture. And more generally, I mean, we didn't do the analysis for lower dimensions. I mean, one could do the same of obtaining the BPS gap in 5 n = 1, for example. And in that case, it would really map just to this same problem, because then the BPS mass, the mass of the BPS states is set by the overall volume of the Calaveras. So we have this observation that, notice that it's precisely, so if the BPS gap behaves as the species bound, then one recovers exactly this linear behavior that one has for the Tadpole conjecture. And if one recovers that the BPS gap is larger than the species bound, as we obtain in 6D, then one obtains something that is even stronger than the Tadpole conjecture. So it goes in the direction of satisfying this conjecture and not stabilizing all the moduli. Of course, this is just a tendency, no? As you can see, these are plots, you have different points with different values, and this is just telling you like the overall tendency, no, for the Calaveras. I mean, and you can have specific models which have some different value. But the tendency is the same that the Tadpole conjecture says. Okay, so this is it. So let me conclude. So we are interested in bounding the number of modes. We have not solved the problem. We are trying to make progress in this direction. You could think that black hole arguments could help, but actually they only bound the number of fields in terms of the cutoff. While in string theory, we expect something stronger, no? Like in the same way that we expect to have a finite number of Calaveras. So in order to study what is the behavior with the massless modes, we go to this deep interior of the moduli space, in which we push everything as high as possible. And then we have analyzed the maximum value of the cutoff set by the BPS states in large classes of supersymmetric compactifications. In such a way that the result is that the BPS mass gap indeed depends on the number of massless modes and decreases with the number of massless modes, but with a bigger slope than the species bound. And one possibility, I mean, there could be others, but one possibility is that this discrepancy is solved precisely because there is a finite number of solutions that I can have. And this is the, yeah, as I said, like, I love to study the asymptotic boundaries of the moduli space, but from time to time, it's also nice to go to the deep interior and to see what surprises we can learn from that. So thank you for your attention. It's above. So the slope is bigger. Yes. I mean, of course, there is an overall factor that they cannot determine. But what we can determine is that the slope is bigger than the slope of the species scale.
What do you mean that, okay, if I have a cutoff that is above the species scale, I will say that this is bad because I will run in trouble with the black hole argument. But if I have a cutoff that is below, do I run in trouble? Must be it's saturated. It's necessary that the cutoff is precisely at the species scale.
So this has the, yeah, so here I have in mind that at the species scale something is happening. That is not just a bound on the cutoff, but that is it's giving you information about a physical cutoff. Like, for example, asymptotically, we know that the species bound corresponds to the Planck scale of the higher dimensional theory in the compactification, or to the string scale. So I expect to have some meaning also in the deep interior. So that's why, yeah, if it's not set by the BP states, we think maybe it's set by other non-BP states that could lie below, and we have not been able to compute. If it's above, it's like there is, I mean, we don't expect to have since these strings are non-mutually local, we don't expect to have a local quantum field theory description above this BPS cap. So what is going on there? Yeah.
Maybe the question was that the species scale is somehow self-regulating. So if you have many states below it, then you just change what the species scale is. So it will always track where the first tower appears. Maybe that was the example that you were
If,
It's not a problem like having lots of states below the species scale. If you follow this BPS line and go below the species scale,
it should be self-consistent in the end.
change the species scale, yeah.
So it should be self-consistent. So I mean, you can just check the mass of the states and see. I mean, and the question is whether you expect to have some physical state, no, at the same scale that would be predicted by the black hole arguments. Principle, yes. We didn't exclude, it's just more difficult. So we have to go little by little, step by step.
Okay, because you could have also other BPS states other than particles.
Yeah, then you have to think of the strings and the membranes because you don't have, yeah, I mean, if you think of four supercharges, you don't have BPS particles. And you can also study, I mean, it's just that, yeah. We really need to study, it's not at the asymptotic boundaries, it's at the deep interior of the moduli space. So.
Thanks for the nice talk. There is something I don't understand. So the numerical values of the entries of the intersection matrix depend on the base I choose. So when you use this information to put a bound on the fields, which base are you working on?
Yeah, of course. I mean, in the end, the result is base independent. You just have to do it carefully. Here, I'm thinking, yeah, like I have the tension, right, in terms of the Kähler parameters, and the volumes of the curves are linear combinations of these Kähler parameters. So that's the basis. Maybe it's not necessarily the most natural base. Oof, that was too fast. Well, it depends. Yeah, with the Tadpole conjecture, there's also this discussion of the two bases and so on. This is the one that, from a geometric perspective, when you know the Morricone, I think it's easier to compute. But
So it's base independent.
the result, yes, is base independent. It's just, I mean, it's just going to depend, I mean, you're just going to change what is the estimation of the point in the moduli space, no, at which you get the maximal gap. This is some t that grows with n, so the definition of this t is attached to the definition of the intersection numbers, no? And then one reabsorbs into the other. Yeah, no, that's a good question. I don't know. I mean, it's just because here the Morricone is very well known. I mean, it would also be interesting to study in 5D n equals 1 where there is an upper bound and a lower bound for what this Morricone is and get the two estimations. I was thinking that it's I don't know. My opinion is that I don't think it's I think it can be representative, and therefore maybe one can use also this to, I don't know, to estimate it in other cases, no? Like to think that the BPS gap is going to be always a bit above this species bound result, and that gives you an estimation of the overall volume in terms of the Hodge numbers. That would be nice to check then in examples. But yeah, I mean, the next step would be to check other Calavillaos, other lists of Calavilla, like the Crosser-Stark list and so on. So in the plot, I didn't say, but I mean, here, so here is just with H11, but I didn't add it. No, yes, this one. Here we take into account also like all the other, like the hypermultiplets and so it's not just in terms of H1, it's in terms of all the massless modes that you can estimate precisely because you know what happened with the superconformal field theory strings. Yeah. Here is summing over all of them, not only the tensors. Yeah. You cannot see now, but yeah. When I put n massless, it's not it's H11 plus blah blah blah. That with anomaly condition and so on, you can estimate. Good questions. Good. Say again?
Like any statistical significant measure for this fit, like correlation coefficient of the line, something like that.
You mean beyond the slope?
Beyond the point estimate.
Yeah, no, not really. We didn't do more than this. Yeah, just like to get the distribution, no? You mean? No, we don't have it. I mean, it can be interesting, yeah, like if you want to know like as I said, this is the tendency, but it doesn't mean that maybe there is some example, no, which has a much larger cutoff, and maybe therefore you can stabilize all the moduli there, or like, yeah, it depends on the distribution, but that's getting into more details than what we did.